let us say that we know the variation of field along a line. As we have discussed, that potential difference between 2 points will be equal to the negative of the line integral of field along this path, as this term represents the area under the field graph. So potential difference between 2 points is the negative of area under the field graph between these points. Now, if we move a small distance along this line, then the small change in potential is equal to this term. Rearranging this equation, we can say that the field at a point along this line is the negative gradient of potential at that point along that direction. That is, if we plot the potential graph along an axis, then the negative of the slope of potential curve at a point gives the electric field at the point along that axis. Please note that function of potential along an axis gives us the component of electric field along that axis only. So in order to find the component of field along an axis, we should know the function or variation of potential along that axis. So if function of potential along x, y, and z is known to us, then the field is given by the negative gradient of potential, which is represented by partial derivatives. Here this term means that we take the derivative of potential with respect to x, assuming that y and z are constants. Similarly, this term means the derivative of potential with respect to y, taking x and z to be constant. And similarly for this term. In order to understand what partial derivatives mean, let us consider a function of x and y. So at any point x, y, value of function is specified along z-axis. So the function will be a surface in 3D space. Now, what can we say about the slope of surface at a point? Well, if we try to draw a tangent line, then there is no single tangent line at this point. Where each tangent represents the slope of surface along that direction. However, all these lines will lie in a plane. Which can be said to be a tangent plane to this surface at this point. Now, if we take the cross-section of this surface with respect to y-axis, then the tangent at this point in xz plane will have a unique value. This cross-section with respect to y-axis means that we have taken y to be constant while we measure the slope of curve in xz plane. This is the partial derivative of function with respect to x when y is taken to be constant. Similarly, if we take the cross-section of this surface with respect to x-axis, then the slope of the curve at this point with respect to y-axis. Gives us the partial derivative of function with respect to y, taking x to be constant. Using these two slopes together, we can say that the slope of the tangent plane at this point will be the vector sum of the slope of these tangent lines. This is what is meant by partial derivatives. Extending this logic for a 3D function, we say that the partial derivative of a function is equal to this term.